Hello, everyone. This is Jennifer Huestis,
And I'm Anderson Taylor.
and we are computer science majors at the University of Tennessee at Martin. Our project this semester is flight control software. We are working in conjunction with the Aero Design Team at UT Martin, who will be competing in the SAE International Aero Design East competition. This is broken up into two parts, knowledge and validation events. The knowledge portion is a written design submission and oral presentation done by the engineering students at UT Martin. And the validation event is composed of passing a technical inspection and safety inspection of the delivery aircraft and gliders. Then we will submit a proof of flight video before the in-person competition in Lakeland, Florida.
All right, so the competition more or less consists of a primary aircraft that holds 3 gliders, like you can see on the right, underneath its wings, and we will take off from the runway and we will make 2 passes over a drop zone. And the object is to drop the gliders at some point during our downwind pass, and the gliders must navigate themselves safely to the drop zone. And then the third objective is that the primary aircraft will drop a payload in the drop zone as well. And all of that needs to be done autonomously. The scoring of the competition consists of much more simply than this equation, is however many gliders make it safely with the ping pong balls intact inside of them, which counts as colonists that would survive in our colony, which is our drop zone, and then supplies, which are dropped from the primary aircraft in its payload. And it's scored based on how much of that survives and how many days of habitability you have at the end of the event.
Here we have a photo of the previous Aero Design team who competed in the spring of 2020. And in front of them, they have their delivery aircraft that they competed with. The next photo is of the spring 2019 competing Aero team. And as you can see, their flight results showed that they were 5th internationally and 2nd nationally. We hope to do better than this and maybe even place first. My contribution to the spring 2021 competing Aero team is a converted autopilot code for the gliders into MicroPython, as well as a driver code for the primary aircraft, PA, or otherwise known as the delivery aircraft, in MicroPython.
And my contribution was to establish network communications between the primary aircraft, the gliders, and the ground station that we use to control it all. I also developed a web page for real-time data observation and flight control, and then a database for flight data review. Currently, the software we're using and have used is ESP-IDF, which I use to recompile the firmware for our wireless chips to allow them to have a longer range Wi-Fi protocol enabled. Then we use Mapbox.gl JavaScript. I chose this over our rejected software of Google Maps API because it allows me to have maps offline and just a lot more control without having to check in with Google servers all the time. Third, I used Flask to run our web server with Python off of a Raspberry Pi. I chose to do this over what I previously thought I wanted to do, which was use Kivy as a framework to make a GUI that would run directly on a Raspberry Pi. But I ended up going with Flask so that we could have a web server interface and a lot more access to people who maybe don't have a connection to the Raspberry Pi directly. For hardware, we're using a Wi-Fi 3.0 and Adafruit Huzzah 32 Feather. Both of these modules contain an ESP32 radio, which allows us to have the long-range Wi-Fi capabilities that we need to get the telemetry at the data rates and the distance that we need. In the past, we used LoRa radios, but the data rates were just too low, and they have a lot of issues with confliction on the same channel when you have more than one radio going at the same time. So we opted not to do that this year. As for programming languages, we're using Python 3 on the Raspberry Pi and MicroPython on the hardware that's on the gliders and in the primary aircraft itself. And that's a change from last year where we used Arduino, and it's a very good change. The challenges we had along the way were primarily deciding on the hardware to use for network communications, because that was a big point of contention, having to rewrite everything to use Wi-Fi as opposed to LoRa radios. Uh, then getting an internet-based map inclusion versus an offline open source map. It's quite difficult to get a map running with satellite images offline and not pulling those images from a server. So that took a bit of work. They enabled the long-range Wi-Fi protocol on the networking modules. This was a lot of work just because all the firmware is written in C, and it takes a long time to get in there and dig through it and then recompile it. And then finally, writing network code that was efficient enough to accommodate the telemetry we need from 4 devices at once, all coming into a single dual-core module and into a Raspberry Pi.
Some challenges that I faced while coding was finding similar libraries for the Adafruit modules in MicroPython versus Arduino. Then there was the built-in map function for Arduino is not included in MicroPython. So I had to make a map Arduino function to take over that built-in map functionality that Arduino has, and that's what I based it off of, their implementation. And then another challenge was just testing autopilot code functionality is hard because we're waiting on the delivery aircraft to finish being made by the engineering students. So we can't test the autopilot code of the gliders until we can drop them. The differences in the glider autopilot software in Arduino versus MicroPython include different libraries to interface with the hardware. Before, with Arduino, it was C++ based. So when we switched to MicroPython, everything is Python based. So we needed to find all new libraries. We also have simpler pin initializations for the Adafruit modules in MicroPython. Basically, the libraries do a lot of those pin initializations for us. They will choose the pins versus us having to label each pin that we need to do, which was in Arduino. We also have the inclusion of the map Arduino function instead of the built-in map function, which does a lot of calculations for us in the stabilization function. Then there's less initializing necessary in MicroPython than in Arduino. This is another thing that is handled a lot inside of the libraries that we include in MicroPython versus Arduino, where we had to initialize every bit of information that we needed to get the modules running inside of the void setup function. We're also using the ESP32 radio instead of the RFM95 radio for networking. The ESP32 radio is for the Wi-Fi modules, and then the RFM95 radio was with the LoRa radios. The last thing is the inclusion of threading in MicroPython. Threading is a huge help with MicroPython because instead of going sequentially in our void loop in Arduino, now we get to run multiple functions at the same time with our MicroPython implementation.
And that's a really big benefit for us because in Arduino, if anything went wrong in any of our functions at any point during the flight, the entire flight came to a halt and the glider would just fall out of the sky because we were single threaded there. By using MicroPython and these new modules, it allows us to not have that issue anymore. So that if something goes wrong, everything doesn't go wrong.
Here we have a flowchart of the glider autopilot code. First, we import the necessary libraries. Then we initialize any variables we have, global variables included. And then we step into our main function, where we start a few threads. The first thread is for the GPS function. The GPS function will read our GPS module, any data that it has, and then it will save that to global variables, and then it will run some extra calculations for us, which is why it is its own function in its own thread. Then we step over to the read sensors function, which is in its own thread, and this reads for the orientation sensor and the barometric pressure sensor, which will update global variables. Then we start the receive data thread. The receive data receives data from the ground station, any commands that are given. Then we step into the send data thread, which will send all of that, the read sensors and GPS, all of those variables that we were updating. It will send that to the ground station so that it knows what exactly is going on up in the air. And then after we've started all those threads, we go to our while loop. In our while loop, when certain state conditions have been met, the stabilization function will be called. This not only stabilizes the glider, but it also navigates the glider to the target. Whenever this stabilization function is called, it will also call the map Arduino function to run the calculations necessary.
This is one of the previous web page displays we had. This was the first one that I made more as a proof of concept and to try to kind of work out how we wanted the layout and what functionality we wanted. And next I'm going to show you the actual version that we have working right now. Our current control panel looks like this. The functionality that we knew we wanted was to have a map that we could interact with to more easily tell our gliders where we wanted them to go. And we also need quick reference, not only for competition reasons, but just for our own reasons. We want a quick reference to our altitude of any of the aircraft that are currently in the air, and their status and their location, which will be a coordinate grid. Next, we have the interactive map. This is using the Mapbox GL. This is actually the airfield that we practice at most of the time, and I've got it set up to where we can just click on the map, and it will populate our latitude and longitude fields, and we can set that target, and it will tell all the gliders that this is your new zone. Next, we have the system connection status. This tells about our networking, if everything's connected or not connected, and a ready for takeoff button, which tells the system, okay, everything's ready for takeoff. Next, in our primary aircraft, we have our flight mode switches, which manual is controller, like manual controller. Assisted is essentially we control takeoff and landing, but it flies itself once it's in the air. And then autopilot is full autopilot from takeoff to landing. And the glider drop status just tells us if the gliders are dropped or not. And a button to drop all the gliders at the same time. Next, we have the 3 glider control panels. Each of them are the same. We have a distance to target, a current heading, and a battery percentage, and a drop glider button for each one in case something goes wrong and we need to drop one individually. And finally, an abort button, which will allow us to abort a flight if it's about to cause harm to someone or crash into a car or something like that. This essentially just makes it do a straight down nosedive. And the final thing is up here in these windows, we get a live rendering of what each aircraft is doing based on the sensor data that we're currently getting. So in my hand, I have the brain for glider 2 here, and you can see that as I move it, we get live updates as to how the orientation is changing. And that's just a nice little thing that we can use to more easily visualize what's going on mid-flight, and later on we can use it to diagnose any issues that we have. The objectives we have completed at this point in time are we have the hardware requirements researched and fulfilled. We have functional network controls between all components. We have the glider autopilot code translation and revision complete. We have the first implementation of the primary aircraft driver code, and we have browser-based flight control and telemetry.
So the progress to be made on the project by the deadline in the spring, which is competition. We want to test the glider autopilot code pre-flight to improve the reliability of the gliders. Then we want to revise the PA driver code whenever the airframe has been completed to get it the best that it can be, as well as refining navigation, the web page, network communications. And then we want to include a database for flight data review. And then the last thing is having test flights.
Very important.
Any questions can be directed to our emails, and you can always look at our GitHub repository if you have any further questions about our implementation.
Thanks.